In the early 1960s, the container had already proven its economic value. Its use reduced ship turnaround time, lowered cargo losses, and reduced reliance on manual labor. However, container shipping still did not exist as an integrated system. It remained a collection of local solutions that developed independently and were often incompatible with one another. During this period, the container had no single set of dimensions or unified structural logic. In the United States, Matson Navigation Company used 24-foot containers optimized for Pacific services. Sealand Service operated 35-foot containers that suited its domestic logistics. United States Lines employed its own formats, further deepening fragmentation. In Europe, container formats were adjusted to railway clearances and national transport restrictions. In Japan, formats were shaped by port infrastructure and domestic transport patterns. The container existed as an idea of universality, but not as a universal technical object. This fragmentation was possible because of the first-generation fleet. Most early container services were handled by converted general cargo ships and tankers. Their holds remained universal spaces, and the container was only one of several cargo types. Stowage was ensured by lashings and temporary arrangements, without a rigid link to the ship's geometry. Under these conditions, the system had no internal force pushing it toward unification. Ships accepted different container formats, ports were not yet fully specialized, and container terminals were still emerging. Containerization developed as a set of parallel experiments, each effective only within its own logistics ecosystem. By the early 1960s, these limits became obvious. Volumes grew, regular liner services appeared, and supply chains became more complex. The lack of standardization began to slow development. Every expansion required individual solutions and raised costs. A real break could occur only at the level of the ship. The ship was the only element capable of physically imposing geometry and rules. At that moment, the containership ceased to be an adapted cargo vessel and began to form as a specialized engineering object. This became the starting point of the second generation of containerships. In 1964, Australia brought into service Kooringa, a ship commonly regarded as the first purpose-built container ship designed from the keel up exclusively for container transport. It was built in Adelaide and entered regular operation on the domestic route between Melbourne and Fremantle. At the time of construction, Kooringa did not impress by size. Her length was about 144 meters, beam about 21 meters, and deadweight roughly 10,000 tons. The ship did not operate on ocean routes and was not conceived as an instrument of global trade. Yet precisely this limited scope defined her historical role. Kooringa's superstructure was located toward the aft part of the hull. This was a practical solution for early containership architecture. It allowed long, straight hatch openings and a maximally clear hold space with minimal interruptions. In that era, there were no firmly established containership layout rules, and each solution was validated by real operation. Kooringa's key innovation was her hold architecture. The ship was designed as fully cellular. Below-deck vertical steel guides, cell guides, formed rigid container cells. A container was lowered into a cell from above and held in place by the ship's geometry without the need for traditional hold lashings. This represented a fundamental change in the container's role. It ceased to be cargo that was simply placed and became an element of the ship's structural system. Kooringa's holds were no longer a universal volume. They were a matrix that accepted only a defined geometry. At the time she entered service, her capacity was not expressed in TU. It was described in terms of container positions for local formats used in the Australian service. Only later, after international standards emerged, did correct comparison become possible. In retrospective conversion to ISO Series 1, Kooringa's container capacity is estimated at about 335 TEU. This figure reflects practical operational capacity without hypothetical deck stowage schemes that were not used in real service. Kooringa did not become a prototype for large ocean container ships. Her importance lay elsewhere. She was the first to demonstrate that the ship could and must impose rules on the container. From this point, the path toward a specialized container fleet became irreversible. By the mid-1960s, containerization reached a boundary beyond which regional solutions stopped working. Container transport moved beyond coastal routes and demanded stable intercontinental service under a rigid schedule. At this point, the container ship began to be seen as an element of a global liner system rather than a standalone ship. In 1966, United States Lines introduced American Lancer, a purpose-built container ship designed for regular transatlantic service. This was a qualitative shift. The ship was created not for experiment but for an ocean route with a fixed timetable. Transatlantic liner service allowed no compromises. Regular sailings, synchronization with ports, and coordination with inland transport required stable speed and a predictable cargo geometry. That is why American Lancer was built significantly larger than earlier purpose-built ships. Her length exceeded 200 meters and beam was about 27 meters, enabling fully cellular holds with cell guides. The ship was powered by a steam turbine propulsion plant, typical for high-speed ocean services of the time, where speed and reliability outweighed fuel economy. Crucially, American Lancer was not a one-off project. She belonged to the C7 series of American container ships built as a class for intercontinental operation. Alongside her worked American Legion, American Liberty, American Lynx, American Lark, and other sister and class-related vessels. This serial approach allowed United States Lines to build an interchangeable fleet with the same speed profile, hold architecture, and operating logic. At the time she entered service, American Lancer's capacity was not expressed in TU. Design documentation used container slot counts tied to the operator's formats. Only later, with international standardization, did accurate comparison become possible. In retrospective conversion to ISO Series 1, American Lancer's capacity is estimated at 1,200 to 1,300 TEU, which became the typical scale for second-generation ocean container ships. With American Lancer and her sister vessels, containerization definitively moved to the intercontinental level. The container ship became a central element of the global logistics chain. At the same time, these ships revealed the limits of the second generation, propulsion, layout, and the constraints on capacity growth, limits that by the late 1960s already demanded a new stage of development. The emergence of the second generation of container ships changed the very logic of container transport. Where the container had previously remained an autonomous unit that a ship tried to accept, fully cellular designs reversed the relationship. The ship began to dictate the rules. First-generation ships retained universal hold geometry. Containers were carried alongside other cargo, often using temporary guides, dunnage, or lashings. This offered flexibility, but it did not deliver speed, repeatability, or scalable growth. Second-generation container ships took a different path. Their holds were designed as a rigid spatial structure intended exclusively for containers. The key element of this architecture was the cell guide vertical steel guides integrated into the hull's structural framing. They formed cells in which containers were stacked strictly vertically, occupying only one permissible position. In the 1960s, there was no separate ISO standard governing the construction of cell guides. Their geometry was determined by practical factors: existing container dimensions, operator experience, classification society requirements, and hull strength calculations. Yet the absence of a formal standard did not mean the absence of standardization. Cell guides became a physical enforcement mechanism. A container that did not match the cell geometry simply could not be loaded. The ship no longer adapted to the cargo, it rejected it. That is why incompatible container systems began to disappear not through agreements but through operational impossibility. Cellular holds also transformed cargo operations. A container was no longer manually placed. It was lowered into a defined position. This increased port productivity, reduced dependence on individual dockworker skill, and lowered the risk of damage at sea. Container transport began to function as an industrial process with high repeatability. It is essential that standardization at this stage flowed from the ship, not from the container. Second-generation ships created geometric boundaries into which container formats were forced to fit. International standards at the end of the 1960s largely formalized a practice that had already been established in the fleet. Alongside advantages came limitations. Rigid hold architecture removed versatility and made the ship fully dependent on the container system. Yet precisely this loss of flexibility enabled scale. The fully cellular containership became an instrument of a clearly defined transport logic.